All right, everyone, welcome to another office hours. In this office hours, we're going to be going over a kind of a long problem, but I wanted to show off kind of how we can use our four-step force problem solution method to solve problems involving uniform circular motion and centripetal force. So before we get into the problem, I wanted to do a quick review of kind of some of the concepts. And so to start with, we need to remember that objects undergoing uniform circular motion are subject to a very specific constraint, right? We can think back to our initial kind of example where we imagined driving a car at some constant speed v in a circle of radius r, like we've kind of diagrammed here, right? The idea is that if you really want to drive on this circular track at a speed of like, say, 60 miles an hour, right, there's only one specific angle you can turn your steering wheel at, so that you get the exact right steering force so that you can drive in this circle. Specifically, the law of uniform circular motion tells us for an object going in a circle of radius r at a speed v with some mass m must experience a net steering force of exactly F net equals the centripetal force, defined to be mv squared over r, pointed towards the center of the circle. Center of circle. Okay. And so the idea is that whatever the forces at play here are, if we add them all up, in order for this object to be going in this particular circle at this particular speed, we need to have a total net force of mv squared over r pointed exactly towards the center. Otherwise, this object is not actually going in this circle. Okay. And so here's our general strategy when it comes to solving uniform circular motion problems. The important thing to remember is that UCM problems are actually just force problems. The idea is that they have a particular constraint, right? So if we solve equilibrium problems, then we know that the constraint is that all the forces and all the torques add up to zero. This is very similar, but instead all the forces and all the torques, or whatever, well, there's no torques here, but all the forces in this case must add up to F net equals mv squared over r, right? And so the way we solve this is going to be basically our usual four-step process, and we'll kind of have to take a little bit more care when we talk about the constraints. So as per usual, draw FBD. And so we'll start with our free body diagram to understand what forces are at play. Then after our free body diagram, we'll do the usual things and use the free body diagram to write down Newton's second law equations in order to kind of mathematically relate all these forces together. And finally, this is kind of the hard part here, is in the constraint step, remember, we need to constrain the net force. One question we often have to answer here is which direction is towards the center? Oops, that goes after the quote. There we go. The idea is we need to identify what the actual circle that the object is going in is, and that way we can figure out kind of where the centripetal direction is, right? And then the idea is after this, we should just be able to solve as per normal, as long as we have done kind of these other steps correctly, okay? And so let's go right into it with a problem called the conical pendulum. So what I want you to do is imagine a room where there is a ball kind of hanging from the ceiling. We'll call this ball the bob. And the bob has some mass m, and it's attached to a string of length L hanging from the ceiling. And we set this thing so it's swinging, and it kind of draws out a cone in the air. The string is going to make some angle theta with respect to the vertical, right? So we've labeled here in blue. And let's say we know that this thing is making one lap every delta t seconds. So it's kind of going at some consistent rate. such that every lap takes the same amount of time. And so our question is, what is the tension in the string and the unknown angle theta? And so the first thing we can do is talk about why this is a UCM problem. So why is this a UCM problem? The first thing we can recognize is that this thing is going in a circle, right? Going in a circle. And so we know that in the air, right, this thing is tracing kind of a circular trajectory along this kind of flat horizontal plane here. We also know that this thing is going at a constant speed. The reason we know this is because delta t is the same every lap. Right? If it makes one lap every delta t seconds for every single lap, then we know the speed of this thing is not changing at all, right? And so because we know that this thing is going in a circle at some constant speed, we can say something about the net force. We know that the net force has to be mv squared over r towards the center of the circle. Okay, and if we indicate that on our diagram, by the way, this is a really useful thing to do, is just so you can remind yourself of which direction later on when you're kind of doing your Newton's second law equations, that the center of the circle is here relative to kind of this position, right? And so when we get to our Newton's second law equations, we can remember that the net force has to be pointing kind of to the right when our bob is here on the left-hand side of the circle. And so, that means we can go ahead and get started with our kind of usual four-step force problem method, right? And so what I've drawn here for you in the bottom left is a side view of the bob as it's kind of on the left-hand side of the circle. And this is really nice because we can see that the radius of the circle is kind of this section of this right triangle here, right? And this will give us a kind of a much easier diagram to draw a free body diagram with. And so for our free body diagram, we can start with the kind of usual orientating coordinate axes here. And let's look at this object and see which forces are acting on it. So we know that there is a gravitational force pulling down on this thing, right? So we know there's going to be some mg pointed downwards. And we also know that there is a contact force. There's a rope kind of attached to the top of this bob, right? And so that means we know that there's going to be a tension this way. And so just to make sure we kind of have our angles labeled out, I'm going to draw this vertical dashed line. And based on the problem, we know that there's some angle theta here, right? Because these two vertical dashed lines are parallel to each other, then any line that's kind of passing through both is going to have some kind of corresponding angles that we know are going to be identical. And so this kind of upper angle here is going to be the same angle theta as the theta between the vertical and the rope. Okay, and so this will be useful because this is going to allow us to compute the horizontal Tx and the vertical component Ty of the tension, right? And so, good. So now since we've exhausted all the contact and non-contact forces, this is a complete free body diagram, and we can go on to writing our Newton's second law equations. So our Newton's second law equations, remember we should have one for the x and one for the y direction since they're independent. And for the x direction, we can see that there's only one force here, right? It's going to be the tension in the x direction. And so we know this had better be equal to the net force MAX. One thing we can also recognize is that we can write down the tension in the x direction, this Tx, in terms of the angle and the magnitude of the full tension vector T, right? Since Tx is opposite to the labeled angle theta, we know that we can rewrite the tension in the x direction as just T times sine of theta, since sine gives us the kind of relation between the opposite side to theta and the hypotenuse of this right triangle. Similarly, we can do the y direction. And so for the y direction, we see there's a vertically upwards force of t times cosine theta by kind of similar reasoning, right? Cosine gives us the adjacent ty divided by the total tension t. And so we can kind of pull out the y component like this. In this case, we have a second force. We know that there's an mg with a minus sign because mg is pointed downwards, right? And these two then have to sum to may like this. And so because we've exhausted all of the forces that we've labeled on our free body diagram, this should now be a complete set of Newton's second law equations. And so third, we can move on to thinking about the constraints here. Okay, so like I said before, when you're doing UCM problems, the constraints are kind of where you have to be careful. And remember, the question that we're going to try to ask is which direction is like kind of in towards the center. And so this is where this little labeled kind of F net on our diagram is helpful, right? In this diagram here, we know that F net points in towards the middle of the circle, which looks like this on our side view. And so we know that based on our law of uniform circular motion, in this case, F net x must be the centripetal force, which is mv squared over r. We also know, because the bob only describes horizontal circles, that the net force in the y direction must be 0, right? This thing is not moving up or down, it's just moving horizontally, and so there can be no acceleration in the y direction. And so if we substitute those in for the right-hand sides of our Newton's second law equations, our new kind of completed set of Newton's second law equations, filled in with constraints, looks something like this guy here, right? And so what I'm going to do is copy these over, and we'll kind of work on the solve step on the next page here. So let me copy these, and we'll slap them up here. And I'm going to add a little kind of separator because there's some more detective work that we have to do here. Okay, so in principle, right, what we should be able to do at this point is just solve these equations for the tension and theta, which are our unknowns. But something goofy happens here, right? So what I'm going to do here is something that can be useful, which is making a list of all the unknowns in our equations and seeing if we need to do any more detective work to figure out what these unknowns are. So the first two that are easy to catch are t and theta, which are definitely unknowns because the problem asks us to solve for them, right? But if I inspect my equations, I see these kind of pesky velocity terms and this pesky radius term. And technically, the problem does not give us the velocity, or the speed, I should say, not velocity, or the radius, okay? And so what that means is we need to do a little bit of work to rewrite both the speed and the radius of the circle in terms of just given quantities, okay? So let's start with the radius, which is a little bit easier. So what is the radius in terms of givens? Wow, givens. S. Good, okay. So the way we can do this is by looking at kind of the geometric setup here. So we have our bob like this. We know that we have some angle with this vertical line of theta. And so what we want is the radius of the circle this thing describes, right? And so this thing is kind of making horizontal circles. And so the radius is going to be this length here, right? If you can imagine this thing swinging around kind of this vertical dashed line, this is going to be the radius of that circle that we're drawing out. And so we do know what the length of the pendulum is, right? And we can recognize that the length of the pendulum, L, the radius of the circle that it's making, and R. And we can recognize here that L, R, and theta are kind of parts of a right triangle, right? And so we can use our kind of usual trigonometry relations to figure out that the radius R is really just L times sine of theta, since we know theta relates the opposite side, which is R, to the hypotenuse, which is L, okay? And so we have a relationship for R in terms of just kind of the givens, right? L and theta. Similarly, we need to figure out what the velocity is. So what is v? Oops, let's do this. What the speed is, sorry. I keep saying velocity. Speed in terms of givens. Okay, and so for the speed, we can remember that this object is just making kind of circles in space, right? And so in general, the speed is given by the total distance traversed, delta s, over the total time it takes to make one lap, which is delta t, right? And fortunately, we know that it takes a given amount of delta t to make one lap, right? Delta t is actually a given from the problem. And so we need to figure out what the distance the object moves is over this delta t time interval. Fortunately, the shape of the trajectory of the bob is just a circle, and so the total distance it travels must be one circumference of a circle, which is 2 pi, times our now kind of solved for r, divided by the given delta t, like this. And so then we can simplify this by plugging in the expression for r we have from above. So this just reads 2 pi, and I'll write this in blue actually, so that we remember that it's givens. 2 pi times L sine theta over delta t. These look a little bit daunting, but I promise when we do kind of the algebra, you'll find that these actually weirdly simplify to be quite nice. Okay, so now we know that we can write both R and V in terms of just givens, right, from the problem. And so we can eliminate them from our list of knowns, or our unknowns, excuse me. And now we have a system of two equations with only two variables, t and theta. And so we should be ready to solve now. So the first thing I'm going to do is rewrite our equations with these new kind of expressions for V and R plugged in. So on our left-hand side, we have our unchanged t sine theta. But on the right-hand side, this becomes this kind of nasty expression, m times 2 pi L sine theta divided by delta t, this whole quantity squared for the speed. And the radius is this kind of L sine theta here, right? And so let's go ahead and stick with the x equation for a little bit, and let's see what kind of progress we can make simplifying this here. So the first thing I can recognize is that the right-hand side can be a little bit simplified. So what I'm going to do is kind of combine these fractions together. So this will look like if I square the expression in the parentheses, 4 pi squared m L squared sine squared theta over L sine theta times delta t squared. And I've done a bunch of like arithmetic here basically. And so see if you can kind of recover this expression. If you're not sure how I got from this step to this step, you can leave a question in the comments and I'm happy to kind of go through in detail. But for now, I just want to get through the problem and not spend too much time on the algebra. So you have to bear with me here for a little bit. What I can recognize here is that there's an L squared sine squared theta in the top and an L sine theta in the bottom, right? So one factor here and here cancels with one factor of L and sine theta here and here. And then that leaves us with the expression, or the equation, I should say, t sine theta equals 4 pi squared m L sine theta over delta t squared. Then my last thing I can recognize is that actually sine of theta exists on both sides as well. So we can divide both sides by sine of theta, and we recover the nice expression t is 4 pi squared ml over delta t squared, okay? And actually, one thing that we can notice here is that this is actually just in terms of only givens, and there's no more unknowns. So usually we might expect that this expression involves something with theta, and then we have to plug in that value for t, so that equation 2 is only in terms of theta, right? Kind of the usual solve for one in terms of the other when you're solving systems of equations. But in this case, we get this nice coincidence that actually t does not depend on theta at all. We can just solve for it from the x direction. And so this is really nice. That means we can kind of take this expression for t and plug it directly into the second equation for the y direction and just solve for theta that way, right? So what I'm going to do is copy over my y direction equation on my next page here. And then I'm going to copy over this result that we got for t so that we can directly substitute it into this equation and solve for theta. Oops, that was the wrong button. Paste, there we go. Okay, so the first thing I'm going to do with this equation here is take the equation and add mg to both sides. So I'm going to add mg so that the left-hand side mg kind of vanishes and we can slide it over to the right-hand side. Then I can recognize that if I just plug in my expression for t here, I can just solve for theta directly, right? Since t is already in terms of just givens. And so after substitution, this becomes 4 pi squared ml over delta t squared times cosine theta equals mg. After looking at this, we can see that there's a factor of m on both sides, so we divide both sides by m and get rid of these common factors. Then we have something that looks like 4 pi squared L over delta t squared times cosine theta equals g, right? And so now what I'm going to do is move this whole term to the right-hand side, okay, by multiplying both sides by its reciprocal. So what I'm going to do is multiply the left-hand side and the right-hand side by the reciprocal of that big fraction. So delta t squared over 4 pi squared times L.
And so I'm going to end up with these kind of terms on the left-hand side canceling, and we get cosine theta is g times delta t squared over 4 pi squared L, right? And remember, the way that we can get rid of these cosines, these trig functions, is by applying the kind of inverse function to both sides, right? So I'm going to apply the inverse function to the inverse cosine function to the left and right-hand sides. And to the left-hand side is going to read cosine inverse of cosine of theta, which is really just theta, excuse me. And the right-hand side is going to have to carry around this kind of inverse cosine, but it's going to be the inverse cosine of g delta t squared over 4 pi squared L, right? Remember, the inverse cosine is a function that is evaluatable if you know what the inside is. We don't know what the actual numerical values of any of these are since we're doing it algebraically. But that means that because each of the terms inside that inverse cosine on the right-hand side is actually like a known value, we can just leave it like this algebraically and consider the problem solved. So we can write down theta is the inverse cosine of g delta t squared over 4 pi squared L. And now we have written theta in terms of just the given quantities from the problem, okay? All right, there it is. We have done it. We now have the tension and the angle in terms of just given quantities from the problem, right? And so I know there's a lot of algebra here, right? Like we shortcutted a bunch of algebra here. We shortcutted a bunch of algebra all through this disaster. But what I want us to focus on here is really this kind of step 3 constraints bit. The important questions we had to think about here were what was the actual circle that this object was traveling in, right? And we knew that because this was a horizontal circle, we had to set the horizontal net force, F net x, to be mv squared over r. It might be tempting, right, to just set r is equal to L here, but that's not the case. Even though the string is of length L, that's not the actual radius of the circle that the object is traveling in, right? So we need to be a little bit careful here. Other than that, once you get this constraint kind of lined up, technically speaking, all of this is just algebra. And so if you have any questions about any of the algebraic steps, you can feel free to leave those in the comment section below. But I kind of just wanted to emphasize this step 3 bit here where we thought about the uniform circular motion. Okay, that's really all I have for this office hours. If you have any questions about anything we did here, you can leave a comment in the comment section below, and I'll try to get to it as soon as I can. And as per usual, please don't forget to like and subscribe for more free physics problem solving tips and tricks just like these. This has been Physics Tutoring Quantized.